Testing, can you hear me? All right, this video is public now. I hope you guys can hear me. So I did not finish the surface integral chapter. So last time they said surface area of a parametric surface. So if you have a vector valued function defined by parameters u and v, so it's defined like this, then if we have the tangent v, so it's the derivative of the vector valued function r with respect to v, and then there's du, derivative of the vector valued function r with respect to u. So if we do the cross product of these two tangents and derivate them with respect to u and v, then what we get is the surface area. So this gives the surface area for a vector valued function defined parametrically. Yeah. Well, that's what I learned last time. And they use it over here. So if our vector value function x and theta, x f of x cos theta, f of x sine theta, and they use it over here. This time I'm going to be studying about surface integral of a scalar valued function. Now that we can parameterize surfaces and we can calculate their surface area, we are able to define surface integrals. Didn't we already do that? What is this? Surface area. This is surface area, right? First, let's look at the surface integral of a scalar valued function. In Farmini, the surface integral of a scalar valued function is an analog of a scalar line integral in one higher dimension. The domain of the integration of a scalar line integral is a parameterized curve. The domain of the integration of a scalar surface integral is a parameterized surface. Therefore, the definition of a surface integral follows the definition of a line integral quite closely. For scalar line integrals, we chop the domain curve into tiny pieces, chose a point in each piece, computed the function at that point, took a limit of the corresponding Riemann sum. For scalar surface integrals, we chop the domain region into tiny pieces and proceed the same fashion. Let S be a piecewise smooth surface with parameterization RUV with parameter domain D, and let f, x, y, z, so D over here is for u and v, and let f, x, y, z be a function with a domain that contains S. For now, assume the parameter domain D is a rectangle, but we can extend the basic logic of how we proceed to any parameter domain. Divide rectangle D into subrectangles Dij with horizontal width delta u and vertical length delta v. Suppose that I ranges from 1 to m and j ranges from 1 to n, so that D is subdivided into m in rectangles. This division of D into subrectangles gives a corresponding division of S into Sij pieces. Choose a point Pij in each piece Sij, evaluate Pij at F and multiply by area Sij to form the Riemann sum. So Fp delta Sij. Okay, hold on. To define a surface integral of a scalar valued function, we let the areas of the pieces of S shrink to 0 by taking a limit. The surface integral of a scalar valued function of f over a piecewise smooth surface S is so integral f x y z ds limit m into infinity m n f of pij delta sij. Okay, notice the similarities between this definition and the definition of a scalar line integral. The definition of a line integral, we chop a curve into pieces, evaluate a function at a point in each piece, and then let the length of the pieces shrink to 0 by taking the limit of the corresponding Riemann sum. In the definition of a surface integral, we chop a surface into pieces, evaluate a function at a point in each piece, and let the area of the pieces shrink. Let the area of the pieces shrink to 0 by taking the limit of the corresponding Riemann sum. Thus, a surface integral is similar to a line integral but in one higher dimension. But what I'm wondering is, does this calculate the volume? Because it's like f of p, which would be the height times the area of the piece. The area would be delta u times delta v. So does this calculate the volume in 3 dimensions? The definition of a scalar line integral can be extended to parameter domains that are not rectangles by using the same logic used earlier. The basic idea is to chop the parameter domain into small pieces, choose a sample point in each piece, and so on. The exact shape of each piece in the sample point domain becomes irrelevant as the areas of the pieces shrink to 0. Scalar surface integrals are difficult to compute from the definition, just as scalar line integrals. To develop a method that makes surface integrals easier to compute, we approximate surface area Sij with small pieces of the tangent plane, just as we did in the previous subsection. We call the definition of vectors Tu and Tv. So Tu is this and Tv is this. Okay. From the material we have already studied, we know that Sij is approximately this. Well, this still confuses me though. Because these two cross product will give you the area um area made by Tu and Tv, right? The cross product, the magnitude of the cross product will give the area made by Tu and Tv. Yeah. But what confuses me is this part. Therefore, delta S f x y z ds limit m n to infinity. The approximation becomes arbitrarily close to limit m into infinity as we increase the number of pieces Sij by letting m and n go to infinity. Therefore, we have the following equation to calculate scalar surface integrals. So this is equal to this f rub du cross dv dA. Equation 6.19 allows us to calculate the surface integral by transforming it into a double integral. This equation of surface integrals is analogous to 6.7 for line integrals. Hold on. I want to go back to line integrals. I'm still unsure by what this integral gives exactly. And I'm still unsure, like in the derivation, I was confused by this part. They say we scale the tangent vectors by constant delta u and delta v to match the scale of the original division of the rectangles in the parameter domain. This is the parameter domain. Du and tv, you multiplied by du, so you multiplied by du and dv. But I don't understand how it would make it match the thing. And what is this supposed to give? Therefore, the area of the parallelogram can be used to approximate the area of Sij is. So they're approximating the area of this box. But shouldn't TV and TO be it? You want the size of TV to be approximately the size of delta V, right? So shouldn't we make TV tangent first and then multiplied by dV? Oh, sorry, shouldn't we make this tangent a unit vector first and then multiplied by dV? Why are we multiplying it directly? So dV delta V. Hold on, what is the length of SI and Sij? So the domain is divided into intervals of dV, du. How is SI divided? Sij divided? Sij. So I know why TV and TU is used because it like points in the direction of where the grid line is going, right? Okay, let's just skip that. Let's just assume that the equation is this, and then with all that, we end up with this. So line integral gives area. That I know. I think they have a picture here somewhere. Yeah, line integral gives area of this blue sheet, for example. So what does this give exactly? Does it give the area? Does it give a volume? Calculate surface integral this, where S is the surface with parameterization RUB. Okay, let's try this. 6.65. RUV UU square V. S is the surface with parameterization. There's 0 to U, and then 0 to 2, and then 0 to U. Five. Uh, you do this, right? F R U V. But where did the 5 go? Do I just put 5 here? So this is 1, DU 0, 0, 0, 1. So for I vector, these two minus these two. J vector, these two minus these two, which is 1, and subtract all of that. And for the K vector, these two minus these two, which is just 0. And you want integral 0 to 2. We need to find the derivative of this, right? Hold on, let me think. Now we are integrating with respect to dv first. So we introduce v. And this becomes u. Let me think. If I have, let's say, uh, w is equal to u square, then I have derivative of this is like half. This becomes minus half. And then derivative of inside, which is 8w plus 1. I want to see where where the derivative goes. Derivative of the first times the second plus the first times the derivative of the second. Hold on. Plus u or u square plus e to the power of 2. Okay. Times derivative of the inside. Uh, just 8u, right? 8u plus, okay. 8 divided by 2 is 4. 4 times 3 is 12. U root 4u square plus 1. Right. Then 5 integration 0 to u 4u square plus 1. This is equal to 5. It is this divided by 12, right? divided by 12. So it goes from 2 to 0. Um, so first put 2 here. So first 2 times 2 is 4, 4 times 2 is 8, 9. Then minus it with, then we put 0, 1 over 12. Nine, 3 over 2 is 27. Minus 1 is 26 over 12, right? Sixty-five over 6. Close. Okay, so they did get this. Okay, they did get all the way till here. Why is it 17? Uh, u square. So when we plug in 2, 2 square is 4. 4 times 4 is 16 plus 1, 17. Then why did I write 9? 17 cube and then, okay, well, this is the final answer. Whatever this thing is. Scalar surface integrals have several real-world applications. Recall that scalar line integrals can be used to compute the mass of a given wire given its density function. In a similar fashion, we can use scalar surface integrals to compute the mass of a sheet given its density function. If a thin sheet of metal has shape of surface S and the density of the sheet at point XYZ is rho XYZ, then the mass M of the sheet is M is equal to rho XYZ delta S. Then what is density? Density in this context, what is it? Is it like mass per area? A flat sheet of metal has the shape of surface C is equal to 1 plus x plus 2y that lies above rectangle 0 between 0 and 4 and 0 and 2. If the density of the sheet is given by rho xyz x squared yz, what is the mass of the sheet? Example 6.68. So rho x y z x squared yz. Um, 1 plus x plus 2y. trying to shift. X goes from 0 to 4. And then 0 to 2. Hold on. Just wait a minute. All right. So we have this, we have this, we have, and I should write down the equation. So it sticks with me. S F X Y Z. D S. And hold on, I want to. Oh, there it is. D F R U V. The tangent. I should write R. Actually, yeah. Tangent U. Tangent V. DT. DA. So Z is this. Rho is this. Um, Rho is the function, right? Rho is equal to XYZ. We will treat this as the RUV, right? XYZ over here has the shape of the surface C is equal to 1 plus X plus 2Y. That lies above the rectangle 0x4 and 0y2. The density of the sheet is given by this. What is the mass of the sheet? So R is what describes the sheet, right? F is like the function you're applying. So wait, R U V U V 1 plus U plus 2V. The U 1 0 1 2 So for I, these two minus these two. J, these two minus these two. K, these. Oh wait. For J, it's this times this minus this times this, and we multiply the whole thing with minus. For K, it's this times this minus this times this. Yeah. Now minus 1 square 4 1 6 root 6. So we have root 6 for this. And now x square yz is the function we are applying, right? X square 1 plus 2y dA x cube by x 2x square y square. But I want to know if I'm heading on the right track. Yes, yes, yes. I think the thing that confuses me is what I'm supposed to take as R and what I'm supposed to take as F. Integrate, let's integrate with respect to y first. Or should I do x? Let's do x first. 0 to 2. Y goes from 0 to 2. Um, so when there's 0, no effect. When there's 4, we have 4, 6. Is it 64? 4 cube 64 over 3. 64 over 3. What is this? 256. 256 over 4. Actually, it's just 64. So over 4 disappears. 64 times 2 over 3. Okay. V over 3 doesn't do anything. 128. Three times 2 is 6. 32 y square. 3 times 2 is 6. No. 3 times 3 is 9. times it by 2 square, 4 times 4, 128 over 3, 32 times 4, 128. 128, 4 cube, 2 cubed, or 128, 2 cubed over 9. 1024 over 9. Yeah, whatever the sum is. Orientation of a surface. Recall that we defined a scalar line integral. We did not need to worry about the orientation of the curve of integration. The same was true for scalar surface integrals. We did not need to worry about an orientation of the surface of integration. On the other hand, when we defined vector line integrals, the curve of integration needed an orientation. That is, we needed the notion of an oriented curve to define a vector line integral without ambiguity. Similarly, when we define a surface integral of a vector field, we need to define the notion of an oriented surface. Oriented surface is given as an upward or downward orientation, or in case of surfaces such as a sphere or cylinder, an outward or inward orientation. Let S be a smooth surface for any point xyz on S. We can identify two normal units n and minus n. If it is possible to choose a unit normal vector n at every point xyz on S so that n varies continuously over S, then S is orientable. Such a choice of unit normal vector at each point gives the orientation of a surface S. If you think of a normal field as describing water flow, then the side of the surface that water flows toward is negative, and the side of the surface at which the water flows away is the positive side. Informally, a choice of orientation gives S an outer side and inner side. Closed surfaces such as a sphere are orientable. If we choose the outward normal vector at each point on the surface of the sphere, then the unit normal vectors vary continuously. This is called positively oriented orientation on a closed surface. We could also choose the inward normal vector at each point to give an inward orientation, which is the negative orientation of the surface. Portion of the graph of any smooth function z is equal to fxy is also orientable. If we choose the unit normal vector that points above the surface at each point, then the unit normal vectors vary continuously over the surface. We could also choose the unit normal vector that points below the surface at each point. To get such an orientation, we parameterize the graph of f in the standard way. Rxy is xy f of xy, where x and y vary. Then tx is this and ty is 0, 1, fy. Therefore, the cross product is minus fx minus fy and 1. The smooth orientable surface with parameterization RUV for each point RAB on the surface, vectors tu and tv lie in the tangent plane at that point. Vector tu cross tv is normal to the tangent plane at RAB and is therefore normal to S at that point. Therefore, the choice of unit normal vector is tu cross tv and then the magnitude given orientation of the cylinder. So 6.69 x square, y square, r square. From C0 to H. Um, Wait, I will draw a hat here. XY is the radius r cos x. From 0 to H. Wait, how do I do this? From 0 to H. U, V. Uh, U is this. I, U, and then V. There. What do they want? Orientation? TV is 0, 0, 1. So the orientation would be this times this minus this times this. This times this minus this times this, but negative of that. And for k, it would be 0. Hold on, let me think about it for a minute. All right, this is one orientation, and the other orientation is when I multiply it with a negative 1, right? I need to find the normal. So this is this square plus the, hold on. Should one of them be cos? So for you, it's this. For this times this. Sorry. This times this minus this times this. So this is supposed to be cos. Why is it my... yeah, yeah. Actually, yeah, it's just r. And then n is equal to... hold on, cross product is not the... okay, okay. Notice that all vectors are parallel to the xy plane, which should be the case with vectors that are normal to the cylinder, given orientation. The other orientation would be the negative of this, right? Since every curve has a forward and a backward direction, it is possible to give an orientation to any curve. Hence, it is possible to think of every curve as an oriented one. This is not the case with surfaces, however. Some surfaces cannot be oriented, such surfaces are called non-orientable. Essentially, a surface it can be oriented if the surface has an inner side and an outer side, or an upward side or a downward side. Some surfaces are twisted in such a fashion that there is no well-defined notion for an outward or inner or outward side. A classic example of a non-orientable surface is the Mobius strip. Okay, so there's no defined inward or outward side. In the idea of orientable surfaces in place, we are now ready to define a surface integral of a vector field. The definition is analogous to the definition of the flux of a vector field along a plane curve. Recall that if F is a two-dimensional vector field and C is a plane curve, and the definition of flux of F along C involved chopping C into small pieces, choosing a point inside each piece, calculating F dot n at the point. The definition of a surface integral of a vector field proceeds in the same fashion, except now we chop surface S into small pieces. Choose a point in the small piece, calculate F dot n at that point. To place this definition in a real world setting, let S be an oriented surface with a unit normal vector n, and V be a velocity field of a fluid flowing through S. And suppose the fluid has density rho. Imagine the fluid flows through S, but S is completely permeable so that it does not impede the fluid flow. The mass flux of the fluid is the rate of mass flow per unit area. The mass flux is measured in mass per unit time per unit area. How could we calculate the mass flux of the fluid across S? Okay, this is going to be long. The rate of flow measured in mass per unit time per unit area is rho n. To calculate the mass flux across S, chop S into small pieces Sij. If Sij is small enough, then it can be approximated by a tangent plane at some point P in Sij. Therefore, the unit normal vector at P can be used to approximate n xyz across the entire piece Sij, because the normal vector to a plane does not change as you move across the plane. The component of the vector rho v at P in the direction of n is rho v dot n at P. Since Sij is small, the dot product rho v dot n changes very little as we vary across Sij, and therefore rho v dot n can be taken as a approximately constant across Sij. To approximate the mass of fluid per unit time flowing across Sij, you need to multiply rho v dot n by p. Wait, what is this? Uh, what is this p over? P is the point, but hold on, what's happening? By the area of S delta Sij, where n, rho, and v are all, okay. This is a function. So rho v dot n at point P. This is analogous to the flux of two-dimensional field F across a plane curve C, in which you approximate a flux curve across a small piece of C with the expression F dot n delta S to approximate the mass flux across S. As pieces Sij get smaller, the sum gets arbitrarily close to the mass flux. Therefore, the mass flux is S times this. This is the surface area of a vector field, letting the vector field rho v be an arbitrary field f leads to the following definition. So we have, let f be a continuous vector field with a domain that contains oriented surface S with a unit normal vector, and surface integral of f over S is surface integral f dot ds is equal to surface integral of S f dot n ds. Notice the parallel between this definition and the definition of vector line integral. A surface integral of a vector field defined in a similar way to a flux line integral across a curve, except the domain of integration is a surface rather than a curve. This integral is called the flux of f across S, just as an integral. This integral is called a flux of f across curve C. A surface integral over a vector field is also called a flux integral. Just as with vector line integral, surface integral is easier to compute after surface S has been parameterized. Let RUV be a parameterization of S with parameter domain D. Then the unit normal vector is given by N is this cross product over this cross product. And from equation 6.20, we have this is equal to this, which is equal to this. So we have this. How much more? Okay, this is the last part. Calculating a surface integral. F is this, RUV is this. Calculate TU and TV and substitute. We substitute these values over here, right? Why is this minus y? We calculate TU, TV, calculate their cross products, and RUV is already given. We substitute U to X, V square minus U to this Y over here, and then we do nothing with U plus V, right? Okay, let's see if they do what I said. TU is 1, negative 1, 1. TV is 0, 2v, 1. The cross product is this. So did this substitute v square minus u over here? They did. Yeah. All right. Calculate mass flow rate. Let the v be 2x, 2y, z represent a velocity field of a fluid with constant density 80 kg per meter cube. Let S be the hemisphere x square plus y square plus z square equals 9 with z more than equal to 0 such that S is oriented outward. Find the mass flow rate of the fluid across S. Velocity is this. Okay. Velocity is the vector field. Uh, we need to define RUV for the sphere. All right. $6.71. To x to y z. X square plus y square plus z square equals 9. Okay, how about we do um it's a sphere, right? It's a sphere. No. This equation. So rho here is 9. Cos theta sine phi. Nine sine theta sine phi. And 9 cos phi. And then we need to calculate TU and TV, right? Hold on. 0 to 2 pi, then 0 to pi. 0 to 2 pi. Why is it only 0 to pi though? Okay, so it's calculating a circle all the way from 0 to pi, right? What if we do 0 to pi from both sides? So So phi, cos phi is 0 to pi, cos phi is 0 to pi. Z is from 0 to pi. No, wait. Cos 0 is 1. Cos pi over 2 is 0. Okay. I understand. But the Z only changes from 1 to pi over 2. Nine cos theta sin phi will change to cos. Nine sin theta sin phi. 9 cos theta sin phi. Then minus 9 cos, yeah. No. This will be 0. Theta, yeah. Because theta is in the xy plane, right? Now, um, uh, this times this minus this times this. Now, this times this minus this times this. It would be plus, right? Because it's in the middle. So 9 square. This times this minus this times this, but because of the minus, it will become plus. So this times this plus this, excluding the minus, times this, right? But the thing is, we have wait, what? Oh, yeah. We have cos theta. So we will get cos square theta. Your sine theta will get sine square theta. So these two multiplied plus these two multiplied, the cos square theta and sine square theta is 1, right? It's 9 cos phi, 9 sine phi, 9 sine phi. Okay, yeah. So we can extract it out. Cos phi, sine phi. Now, I do not know if I'm doing this correctly. We can take 9 out. Cos square theta. plus sine square theta plus cos square this sine square this. Cos square sine square is just 1. Sine square phi. I need to look at the answer. What if I'm working for so long and it's wrong? Okay, it's correct so far, but what about theta? Um, did I calculate 9 cos theta sine square phi? Uh, why 9? Why not 9 square? Oh, the radius is 3. I have to. I have to edit so much. 3, 3, 3, 3. 9, 9, 9. 3, 3. Now that's out of the way. Cos theta sine square phi. Sine theta sine square phi. Sine phi cos phi. But if we try to take this, okay, square of this plus square of this plus square of this, the 9 square goes out. 9 square goes out, it will remain 9. We can abstract, we can like factor out 9 square and then it will become 9. We can factor out sine phi square from this side as well. Sine square phi, sine square phi, sine square phi. We can factor it out and then we get sine phi here. Then we are sine square phi, sine cos square theta, sine square theta. They add up to make 1. So we are left with sine square phi because the other two sines they went out. Then we are left with this, which is 1. So the normal here is we get rid of the 9, we get rid of sine phi. Cos theta sine phi sine theta sine phi cos phi. Yeah, I don't think we need the normal, but we do need this integral. Um, f of RUV, we do that's right. 2xy, 2y, and z. The thing is, how do we get this equation? Do we replace this with x? We have 2x. So we have 6 cos theta sine phi. Two y, 6 sine theta sine phi. And then just z, 3 cos phi. This times it by dot producted with this. This is going to take long. This dot product, 53 sine cube theta. This times this times this. Wait, what? Sine cube. Oh, yeah, cos square and sine square give 1. 3 cos phi, sine, 9 sine phi cos phi. All right. Oh, and we have to multiply the total by 80, right? So the density is 80. In example 6.71, we computed mass flux, which is the rate of mass flow per unit area. We want the flow rate. Instead, we can use flow flux integral, which leaves out the density. Since the flow rate of the fluid is measured in volume per unit time, flow rate does not take mass into account. Therefore, we have the following characterization of the flow rate of the fluid with the velocity v across a surface S. To compute the flow rate of the fluid in example 6.71, we simply remove the density constant, which gives a flow rate of 90 pi meter cube per second. Both mass flux and flow rate are important in physics and engineering. Mass flux measures how much mass is flowing across the surface. Flow rate measures how much volume of fluid is flowing across the surface. In addition to modeling fluid flow, surface integrals can be used to model heat flow. Suppose that the temperature at point xyz in an object is T xyz. The heat flow is a vector field proportional to the negative temperature gradient in the object. To be precise, the heat flow is defined as a vector F is equal to minus K delta T, where the constant K is the thermal conductivity of the substance from which the object is made. The rate of heat flow across the surface S is the object given by the flux integral. Okay. Oh my god. Okay, I will end the stream here then. Should I read? I will read this off the stream. I'll end the stream here then. And um, I will end the stream here, and I will see you guys next time then. Bye.